Okay, chapter 18, Transformers. And I got to start this lecture off with a little story. As you know, in my past life, I was a nuclear submariner. And it's kind of a drag. I mean, it was, some of the stuff I saw was kind of neat. It was interesting. But I would be gone for very, very long periods of time, isolated, totally out of tune with what was going on in the world and pop culture. And there was one year that I was going to be home for the holidays. And I was pretty excited about it because I can't even tell you how many holidays that I was underwater submerged and how many Memorial Days. I remember one Memorial Day I was actually going in the Mediterranean. We surfaced off the Straits of Gibraltar. We had a barbecue in the back of our submarine. We were kind of showing off to the Soviets that, yeah, we're putting another nuclear submarine in the Mediterranean, so there. So anyway, back to my, with me being home for the holidays, you know, I got back and I had some time off, and my wife and I were going, we had 2 kids at the time, we're going Christmas shopping. And I asked my wife, so, you know, what do the kids want? What are they, you know, what are they interested in? And my wife said, my wife said they'd really like some Transformers, you know, and I'm like, when did they first became intrigued with electricity and electronics? What do they want? Step up Transformers, step down Transformers, a pizza match? I had no freaking clue. You're talking about a car that turns into a man? That I don't understand. So anyway, we went out and we found them some Transformers, and of course my kids are grown now or whatever. They wish that they had taken better care of their original Transformers, as they'd be able to sell them now on eBay and make a ton of money. Instead they were, hey Dad, look at this, you know, I'm lighting my Transformer on fire, you know. Which I don't blame them. That was kind of the same thing when I was growing up. Actually, believe it or not, I still have my original Lionel train. It's in a state of disrepair. It still works. But I mean, I used to have that thing. I used to get the track, like put it in an S and then a straightaway, and then it would just like go right over the stairs and down. You know? And if I'd only taken care of that, I probably could have sold that on eBay and retired now, you know, in mint condition. But no such luck. Anyway, we're going to talk about chapter 18, which is our final chapter in ELEC 110, Transformers. After completing this chapter, we're going to be able to describe how a transformer operates, explain how transformers are rated, explain how transformers operate in a circuit, describe the differences between step-up, step-down, and isolation transformers, describe how the ratio of voltage, current, and number of turns are related with a transformer, describe applications of a transformer, and identify different types of transformers. First of all, electromagnetic induction. This is nothing new. The action caused when 2 electrically isolated coils are placed next to each other. The AC voltage is put across one coil, resulting in a changing magnetic field that induces a voltage into the second coil. So what this is like is having an inductor. Remember how we build up that magnetic field? The only thing is we're going to put that magnetic field in close proximity to another inductor, so when the magnetic field collapses, it collapses into the second inductor or secondary winding. The device they use to create this action is called a transformer. Transformers, the coil containing the AC voltage is the primary winding. The coil in which the voltage is induced is called the secondary winding. Now, transformers have what's known as a coefficient of coupling. And it's going to be a number anywhere from 0 to the number 1. 1 indicating that all primary flux lines cut the secondary windings. 1 as in 100%. Make sense? A 0 indicates that none of the primary flux lines cut the windings. If you have bought a transformer with a coefficient coupling of 0, you've done been ripped off. Okay, it's not going to do anything for you because none of the primary flux lines are going to induce any current. The design of a transformer is going to be determined by the frequency at which it will be used, Low frequency, like for power applications, 50 hertz, 60 hertz, 400 hertz, we'll use iron core transformers. And by using an iron core, that helps increase its level of efficiency. Because remember, using a ferromagnetic core will enhance the electromagnetic effect. High frequency applications will use air cores. Because if you use a metal core, sometimes bad stuff will happen with that expanding, collapsing field. You're going to get a lot of molecular shift, and you're going to get heating, and you're going to get losses, eddy current losses, and a variety of different things. So some of these high-frequency transformers, they'll just use air as a core. A transformer is also designed and determined by the power that it must handle. How much power can it handle? And that's going to be measured in volt amps. It's not going to be measured in watts. Don't go to Vetco, identify yourself as one of my students, and ask for a 60-watt transformer. Because transformers are not measured in watts. They're measured in volt amps. Also, the voltage it must handle. Voltage is going to be a factor because of the dielectrics that are used. If you put too high of a voltage across 2 points that are too close to each other, you can end up with arcing. So all transformers are not created equal. High voltage transformers are used for high voltage applications. Transformers, again, are rated in volt amperes. One of the things that you need to pay attention to is what's called the dot convention. The dot convention. If we're looking at a schematic diagram here and there's a dot here and a dot here, that means that whatever you put into the primary will be in phase with the secondary. Typically, the output at the secondary will be 180 degrees out of phase with the primary. This was what I suspect the original transformer did. Because the original transformer in the secondary, you're inducing a voltage based on the collapsing magnetic field created by the primary. So it's automatically going to be 180 degrees out of phase. So say if Lenz's law, right? But what they could do is they could actually put this winding in backwards, wind it backwards, and account for that phase shift. So in a schematic diagram, just look and see if you see the dots. If the dots are side by side, there might not be any dots because it might not be critical. But if there are dots like this, it shows no phase shift. If it's a dot like this, 180 degrees out of phase on a schematic. Transformers are wound with tapped secondaries, what are called tapped secondaries. Center tap secondary is equal to 2 secondary windings. Basically what they do is they get 100% of the secondary winding, and then what they'll do is they'll put a connection into the center. So you got 50% of your winding between here and here, and then 50% of your winding between here and here. Some transformers have multiple taps. And the reason that they did this in the past was so that you could create multiple voltages out of your secondary. So a lot of older legacy equipment was like that, where you'd have a transformer with a primary and then like 8 or 9 secondaries. I remember the last thing that I really remember working on was it was a hi-fi, high fidelity, stereo hi-fi. It belonged to my sister. And this is like back in 1983 or something. And it just stopped working. It was a nice unit for the day. AM, FM, stereo, you know, phonograph player. The whole thing was dead. I get in there, I start looking. Transformer had failed. So it's kind of like, I think that transformer cost like $72. This was pretty expensive back in, you know, but still it was an expensive, you know, it was $500 stereo back then. It's like you put a fifth into it, you know. But I troubleshot it, and I was pretty sure it was a secondary. So I ordered, it was Fisher brand, and I ordered directly from Fisher a replacement transformer, put it in, good to go. The funny thing about it is they had no protective device on it. So when a malfunction occurred, it took the transformer out, pretty expensive piece to take out. So I retrofit a fuse in there to prevent this from happening again in the future. So I don't think she's still using it. So it's kind of old school. Would have been nice if she kept it. Transformers are wound with that tap secondary is also used for power supply to convert AC voltages to DC voltages. Transformer doesn't do the conversion, but a transformer will get a high voltage and then make it a lower voltage so that it can be converted to a DC voltage. The principle that all this operates on is what's called mutual inductance. The primary induces a voltage into the secondary, and the secondary induces a voltage back into the primary. So one of the things, in order for this to take place, and this is not a trick question, but you will see this on some professional exams. This is your source, connected directly to the primary. The secondary has to be connected to the load. If the secondary is not connected to the load, it's not going to induce any current, because current's got to have a place to move. So if this was just an open circuit right here, where would the current go? It's got no place to shake back and forth to, in essence. So you've got to connect the load up to the secondary in order for you to get this mutual inductance. The primary having influence on the secondary. Turns ratio determines whether a transformer is used to step up, step down, or pass a voltage unchanged. And this is, by the way, what transformers are used for. Step up, step down, or pass a voltage unchanged. By passing a voltage unchanged, we call that an isolation transformer. An isolation transformer, isolation is really the #1 reason to use transformers. Keep us isolated from the source. Electrons, that's a good thing. It promotes electrical equipment and personnel safety. The number of turns in a secondary winding divided by the number of turns of the primary winding. This is how we would calculate out our turns ratio. Real simple. NS over NP. N is going to be the number of turns, physically the number of turns. How many turns of wire are there in the primary? How many turns are there in the secondary? A step-up transformer is going to be a transformer with a secondary voltage greater than its primary voltage. And this is going to be expressed as in voltage of the secondary over voltage of the primary, or number of secondary turns over number of primary turns. For this type of a transformer, the turns ratio is always going to be greater than 1. It's always going to be greater than 1. Which means 1 turn in the primary, 2 turns in the secondary. 1 turn in the primary, 2 turns in the secondary. Meaning the secondary is going to have how much voltage as compared to the primary? Twice as much. This is a typo. This should say step-down transformer. Step-down transformer is a transformer that produces a secondary voltage less than its primary voltage. This will always have a turns ratio less than 1. This might be 2 turns in the primary, 1 turn in the secondary. 2 turns in the primary, 1 turn in the secondary. Meaning we put in a high voltage and we get out a proportionally lower voltage. When a transformer steps up the voltage, it steps down the current. Now this here works great in the world of theoretical electronics, fantasy electronics. This is showing that power of the primary is equal to power of the secondary. Power of the primary is equal to current of the primary times voltage of the primary. Everybody understand this math? Straight Watt's law. Is going to be equal to power of the secondary, current of the secondary times voltage of the secondary. What's the only flaw with this? This assumes 100% efficiency and no resistance. You think we get 100% efficiency out of a transformer? Most of the transformers you screw around with in the lab, they may be 60% efficient. I had a student in my class in the past. He worked in aerospace for a supplier for actually satellites. They supplied components for satellites, outer space satellites. And they had a couple transformers, really, really expensive, tens of thousands of dollars. And those were like in the low 90% efficiency. But they were like, you know, precision wound and special, you know, cores. And You don't want to have to buy stuff like that. You don't want to buy replacement parts like that. The current is inversely proportional to the turns ratio. This is expressed as IP over IS. Equal number of turns in the secondary divided by number of turns in the primary. So this is really straightforward. Impedance ratio. One of the big things that we want to do with transformers is what's called impedance matching. Impedance matching is essential so that we get the maximum power transfer from our source to our load. This is why, Mark, in your past life, right, you got 8 ohm speakers, right, you got to make sure that you're matching that to your output. If you're not going to get maximum power transfer. Have all of you heard of that before, like 8 ohm speakers? Okay, you don't want to hook 4 ohm speakers up to an 8 ohm output. You can, and it's going to work, but it's not going to work efficiently. You're not going to get maximum power transfer. In order for you to get maximum power transfer, you have to match the impedance. One of the simple ways of matching the impedance is using what's known as an impedance matching transformer. And an impedance matching transformer, real simple, impedance of the primary, impedance of the secondary is going to be equal to the number of turns of the primary squared over the number of turns of the secondary squared. Applications for transformers include stepping up voltage and current, stepping down voltage and current, impedance matching, phase shifting. The big one, this is the one they're looking for on the examinations, folks, the professional examinations, isolation. Number one reason we use transformers. Blocking DC while passing AC. Can DC make it through a transformer? A DC could make it through your primary, but how is it going to be coupled to the secondary? It's the expanding and collapsing field. So when you turn the DC on, it's going to expand the field. When you shut it off, it's going to collapse the field. So you're not going to be able to couple that DC. So it's great. Keeps the DC on one side, allows the AC to get coupled to that secondary side. And also producing several signals at various voltage levels. This is what I was talking about with a multi-tapped secondary. Multi-tap secondary. Transformers are used for transmitting, and yes, the term transmitting electrical power to homes and industry. Over at the Grand Coulee Dam on the Columbia River, they generate the electricity, then at the substation they run it through a transformer so that the generators are not connected directly to the power grid. That way, if the power line gets struck by lightning, it doesn't take out the freaking generators. They're electrically isolated. One of the reasons they do that is at the power generating plant, they get the electricity, and what do? Do they increase the voltage of the current at the substation over at Grand Coulee Dam? Whatever way you answer, the next question is going to be why. What do? They generate the electricity over at Grand Coulee Dam, and what do? Do they increase the voltage or do they increase the current? Bzzz. Had a 50-50 shot at that one. They increase the voltage. Why? Good answer, but
lower current
what?
passes. You can pass over distance with lower currents.
Yeah.
It's easier to step down than it is to step up, though, right?
No, it's really the same. But the big thing that they're trying to do over at Grand Coulee Dam is what they're trying to do is increase the voltage at the substation so they could transmit high voltage from that side of the mountains to this side of the mountains. By increasing the voltage, what do they do to the size of the conductor? It gets smaller. You need a big conductor to handle a high amount of what? Voltage or current? Current. So by going to a higher voltage, now they could make the wire physically smaller. Higher voltage, and all they have to do is just keep it far enough separated from the other wire so it doesn't short out, and they could bump that thing up to thousands, tens of thousands of volts. Increase the voltage. While they're increasing the voltage, what are they doing to the current? Decreasing it, so they could go with a smaller conductor. Then they bring it to the substation here on the west side of the mountains in your neighborhood, and what do they do to it?
Bring it back down.
They bring it back down, lower the voltage. What does that do to current? Increases the current. They do that so good, they do it again. They do it out on your street with the transformers. Right on your street. They got high voltage going from power pole to power pole to power pole, but then what they do is they lower the voltage going to your home. Lower the voltage, but increase the current. And a typical household utility connection is 200 amps. 240 volts AC at 200 amps. That's the big thing that's the whole way. If you're isolated multiple times, your street gets hit by light, your house gets hit by lightning, it may take out a couple other homes in your neighborhood, period. But it doesn't take out that entire circuit. Doesn't take out the substation, doesn't take out the generator at Grand Coulee Dam, because everything is electrically isolated. The electrons traveling in one loop are simply being shaken back and forth by the electrons traveling in the other loop. You can create a power surge. That happens. Power line gets hit over, coming over the mountains. It may send a spike through the line that could get to your home, because an increase in voltage is going to create an increase in magnetic field, which is going to influence the secondary, but it's not going to be that same amount of current traveling through that secondary loop. It's going to provide you with isolation. Make sense? Auto transformers is a device used to step up or step down applied voltage. We have examples. The Sencor units in here are considered auto transformers. And what they do is they allow you to vary. I saw a couple of you doing some labs in there the other day with that variable transformer. That's what that is an auto transformer. An auto transformer in and of itself does not provide electrical isolation. Both the primary and secondary windings are part of the same core. But those Sencor units also have power isolation. And the reason we have those is so that when you do AC experiments, you're not doing AC experiments plugged directly into the wall. That's a safety violation. You will not plug anything directly into those outlets. If you got to do an AC experiment, plug it into that Sencor power isolation transformer. What about coils on cars? Are coils on cars like transformers?
No.
What does a coil do on a car?
It's only a single coil.
Yeah, but what does a coil do? What is the ultimate purpose of a coil? You have a coil. What does a coil feed?
Distributor to fire your spark plug.
Exactly. And what kind of voltages are you talking about on your spark plug? 5 volts, 8 volts, 10 volts, 120 volts? Thousands of volts, tens of thousands of volts. So how are you going to create tens of thousands of volts under the hood of your car? Last time I checked, there's a 12-volt battery underneath it. And that battery is 12 volts DC. So how do you get 12 volts DC converted into 20,000 volts across your spark plug?
So the coil is like a transformer.
Coil's like a transformer. The way a car coil works is you send a low voltage pulse to it, and it's that pulse, it's that expanding and collapsing field that creates that high voltage spark. So it's not AC per se, but it's a pulse of DC that you're sending into the coil. You have an expanding field, then you have that field that collapses back into the coil winding, and that induces that 10 to 1,000 volt spark that gets sent to your spark plug. But it's DC that originally created it. So I don't know if there's any gearheads here or anybody that's ever thought about it that way, but how do you get a 12 volt DC system in a car to create tens of thousands of volts that go to your spark plug? Well, it's the coil that does it. My great coil story.
I thought about that before.
Yeah. And when you think about it, you kind of go crazy because it is DC. And Joe said DC doesn't work with transformers, but it's DC, but it's put into a pulse. Actually, if any of you are old gearheads and worked on anything like setting the points on your distributor, that point, that contact that it makes and breaks, that basically is what is sending that pulse to the coil to create that. Now it's all done electronically. You've got solid state circuits in there that are, actually, you want to hear the ultimate design? The ultimate design is on my Ford Taurus that I have. I've got the Taurus SHO, super high output V8. Ford had a better idea. What they did with mine is I have coil on plug. So every spark plug has its own coil right over the top of it.
Is that the distributor list?
Yeah, it's all fed directly from the computer. That's great. I mean, it sounds like a great concept. So I have low voltage going to my coil, and then my coil fits right over my plug, right? Except when it comes time to replace these things. Anybody want to take a wild guess at how much my coil costs? What's that?
Per coil?
Thank you. Thank you for adding that. Thank you for adding that.
There are 8 of them.
There are 8 of them. Oh, my wife is ready to freaking kill me. She's like, "Argh." It's one of the things that's special about my car. The retail, if you go to the dealer and get it, it's $250 a coil. And my car takes 8 of them. So the maximum, and a lot of you are going to grunt and groan at this, it takes me, working on my car, 8 hours to get to my rear coils, because the engine is shoehorned in there. And then even with that, I'm bleeding. I'm like, oh, it takes me 8 hours to get back there. So whenever I do a 100,000-mile tune-up and I basically put in new plugs in the back, I buy 4 coils. And because the coils in the back are prone to a lot more heat and failure, but I figure since I'm back there, so you're talking $1,000 worth of coils on the spark plugs.
Not very reliable.
Not with all the heat in the back of the engine, but that's another story. I mean, it's. So I actually got a pretty good price. I bought some I got some last year. There's some of that stuff's not even available now because they don't make that car anymore. They have a new version of it, but they're not even supporting. I've got the active suspension on mine where they got the magnetic fluid inside the struts. So it sends a voltage, and within 1 millisecond, it stiffens my struts as I drive. I had one of those fail, okay? That's a $328 strut. But Ford doesn't make them anymore. So I need one right now. I had failure of that strut. So through a secondary market, somebody in Wisconsin has one, and they're gonna sell it to me. And my wife's like, why didn't you get a normal car? It is kind of normal in an abnormal way. But yeah, I get some, but and all it is a coil. Coil on plug. All it is a piece of wire that low voltage comes in, creates a magnetic field, and when it collapses, it induces that spark. So I'm sure there's probably some retrofits that I could do, but.
It'll make you feel good that one for Porsche is like only $50.
Are you serious? Really? Coil on plug only $50?
We did some research on our fuel injection stuff, and some Cayenne coil on plugs are cheap, super cheap for new stuff.
I wonder if we could modify that
That's
to.
what I was thinking.
Yeah.
Probably retrofit coil on plug.
That help keep my marriage intact. You spent $1,800 on some plugs and some. Anyway. In summary, transformers consist of 2 coils, a primary winding and a secondary winding. Transformers allow an AC signal to be transferred from one circuit to another. Transformers allow stepping up a signal, stepping down a signal, or passing a signal unchanged. Transformers are designed to operate at certain frequencies. Transformers are rated in what are called volt-amperes, not watts. It is power, but we call it volt-amperes. Turns ratio determines whether a transformer is used for stepping up a voltage, stepping down a voltage, or passing a voltage unchanged. And even if you pass a voltage unchanged, are you still going to have losses? Yeah, because transformers are made out of wire, and wire is made out of copper, and copper has resistance associated with it.
And you're still going to have phase shift, right?
And you're still going to have phase shift, unless you wind it, unless it's manufactured to account for that. Step-up transformer produces a secondary winder voltage greater than its primary voltage. That's why it's called step-up. Has a turns ratio that's always greater than 1. Step-down transformer produces a secondary voltage less than its primary voltage. Has a turns ratio that's always less than 1. The turns ratio determines the amount of voltage that is stepped up or stepped down. Transformer applications include impedance matching. That's a big one. Just with a little transformer, you could match impedance. And that's very, very important, especially if any of you get into any audio applications or anything like that. It's extremely critical to get impedance matching correct. Microphones have different impedance associated with them, and then the boards that you're plugging into are different. Got to get that impedance right. To ensure what? Maximum power transfer. Tell you what, you guys got to remember that. When you get to Peter's class, he's going to ask you about what you know about maximum power transfer. And usually students are like, I don't know. Then Peter gets pissed, man. He comes sees me. Aren't you teaching about that? Yeah, I teach them about it, but they're just not freaking listening. Okay? Maximum power transfer takes place when the internal resistance impedance of the source equals the internal impedance of the load. Just always remember that. That's why you want to hook up 8 ohm speakers to an 8 ohm source. Or you don't want to hook up 4 ohm speakers to an 8 ohm source. You're not going to get maximum power transfer. Transformer applications include impedance matching, phase shifting, isolation. That's the big one. For whatever reason, they like asking that in professional exams. Blocking DC while passing AC and producing several signals at different voltage levels. Isolation transformers pass the signal unchanged, used to prevent electric shocks. You'll still get zapped, but how many of you here would like to be connected directly to all the power of the Grand Coulee Dam? Now, so through the use of transformers, you could be isolated from that. It's still going to hurt. It's still going to hurt. But you're not connected. How many of you would like to be connected directly to the 200 amp source coming into your home? But through the use of a power isolation transformer, you can keep yourself isolated from that. Auto transformers used to step up or step down a voltage, and this is like a variable. A lot of people call them rheostats. Yeah, connected to that, rheostat. Right? They're not a rheostat, it's an auto transformer. Auto transformers do not provide us with isolation. However, our models here, the Sencor, is not only an auto transformer, but it also provides us with isolation. That's the whole purpose of that unit. Any questions?
Is there an equivalent to transformer at DC?
No. Because again, with DC, there's no way it's the on and off. If it was a pulsating DC, there would be a way like a car coil. But other than that, no, there's no equivalent. You know, you could use a coil. You got to be real careful though, because again, if it's DC and you're creating a pulsating DC, then conceivably you can use a transformer to couple that expanding and collapsing field from the primary winding to the secondary. But DC in the pure sense of DC, voltage multipliers. And we're going to cover that next in ELEC 120. And in essence, what we're using, believe it or not, is, see how smart you guys are. What component do we use to temporarily store voltage in? Capacitor. In the form of an electrostatic field. So if you could charge up capacitors, right? And then you could take and then connect those temporarily in series with each other, then you could get this voltage plus, and essentially you're getting that DC voltage and you're multiplying it. So multipliers that basically use capacitors as their active component to give you a higher DC voltage out. Because yeah, that is a big challenge in some applications where you want to get a higher level of DC out. What's that?
Car audio amplifiers.
Mm-hmm.
If you're opening one up, there's lots of big capacitors.
Yeah. Question?
No, I was just going to say one of the projects that I'm doing is that same principle. The first step was just one LED with one capacitor, and then it added 2 LEDs, but it added a second capacitor between the first LED and the second LED.
Mm-hmm.
So that basically bumping up.
With an LED, I don't think you have to multiply the voltage necessarily.
Red and blue one requires
Different voltage. Yeah. Yeah. Does anybody have any final questions? This concludes the lectures associated with the LEC 110. So it's up to your class lead. I guess you're on track this week to finish up your final quiz. And then after this, it's just going to be a matter of scheduling the final exam for ELEC 110. Don't forget, got to get all your labs knocked out. Projects are going to be due next week. The 8th, I believe, is the day. And got a lot going on. So tomorrow is June. It may feel like January or February outside. But tomorrow is officially going to be June.